So very beginning, everybody have experience with insulin, your family or friends or whatever. So if we're going to use insulin, what things come up to your mind first?
Blood sugar.
So if you as a patient or as a end user, if you want to use an insulin product, what is the first thing coming to mind?
Injection.
Injector. Diabetes. Surprise me, nobody gonna care about the price. I saw, Mary's last slide all about it's gonna cost. So you first come up and say, what's the cheapest price I can have? For that, right? So this is probably for this kind of the biopharmaceuticals, obviously all pharmaceuticals are very expensive. Okay, but the key thing is right here is how you could manufacture a very cheap product. So that is my job, our job, the bioprocessing company. Okay, we're trying to manufacture this kind of product in very, very large quantity, very cheap price. Okay, but we still have a lot and very high quality. Okay, because that is the patient's safety is the obviously first priority. Okay, so for different from the drug discovery people, they discover very, very fancy product, okay? But ultimately it's down to the job of the bioprocessing people trying to build and manufacture them. If this product cannot be manufacturable, and then there's no value, okay, for that kind of discovery. So this our job is really trying to turn whatever medical discovery to this kind of real product, okay? So just to give you this kind of the insulin here, this is a real insulin kind of the structure around here. I'm sure all of you have some background of biology or maybe I will assume that. So, no, anyway, so this is the amino acids for the insulin. So this is 51 amino acids. So that's the structure we want for the product. But if we know that is very important, but when you come to the manufacturing, we cannot use this only 51 amino acids put into the manufacturing. So what we have to do is we have to add more. We put it here. So if you look around here, we're going to put more kind of this kind of the peptide from here. So that's a kind of herping peptide. So we put this kind of things inside into the bacteria, and the bacteria are going to manufacturing this kind of the this kind of product. And after we get this whole things out, and then we're going to outside, we're going to cut this up, and then we're going to reformulate and restructure this structure and get this restructured product to be real insulin. So that is the one product. So I will give you kind of videos right here. So that is, let me just fix this one. So that is how we turn this one. So basically, you know the structure. We put it into the real manufacturing process. Now we get the product around here, and we're going to inject to patients. The patient will going to say, oh, this is not product I want. I want to have a new type of product. I want the oral. But this is the injection. I don't want injection. I want something very easy one. I can take, like oral. I can take it, or it has the patch. I can start to the skin. So whatever, and then we're going to come back to see what we can do. This is, and we're going to do the cycle and try to improve the product. Okay, improve this manufacturing process. So just give you a video from here, just the.
You might want to just pull it up on this computer if it's working. I did the same problem. You just, Eric, figure this one. You can switch over this one.
What is that tree?
Got what?
I mean, just to look kind of like.
Look at all this, just really experimental different
It's technology. That's representing the house.
Eating the hamster and we're like, you're gonna keep it going.
Like that. So if I think you know what you're referring to, it's just representing the number of amino acids. Oh, so a protein is made up of amino acids.
So that's what apply over to that.
So amino acids make up a protein.
We take you around the world to show you how. On how do they do it? Almost 1 in 10 adults worldwide has a condition known as diabetes. And many of these 400 million people rely on life-saving injections of insulin. But for nearly 50 years, the only insulin available came from cows and pigs. Then a Danish company worked out how to make synthetic human insulin using the key ingredient in a loaf of bread, baker's yeast. So, how do they do it? Welcome to Novo Nordisk in Kalundborg, Denmark. This vast plant covers over 1.3 million square meters, making it twice the size of the Pentagon, the world's largest office building. It needs to be big because they produce almost half the world's supply of synthetic human insulin. Remarkably, they make it using the same stuff that gives rise to your loaf of bread. Dr. Jens Kierkegaard Beck explains.
To make a good bread, you need the yeast. The very same yeast is also used for producing the insulin, saving millions of people's lives.
As Jana Fodlov
Just to hide on, for this yeast, you say that is from from bread. You can use the same yeast, but this yeast has been transformed. You have the insulin genes inside. Now you can express it properly.
demonstrates just for us. All it takes is a tiny amount of yeast to produce enough insulin to treat thousands of diabetics. 1 milliliter in a vial like this can generate enough to save up to 500,000 lives. But this is no ordinary insulin. It's been cleverly genetically engineered by adding the gene for insulin production to its DNA, turning it into a super yeast. The next problem is, yeast is a living microorganism. It needs feeding before it can produce insulin. The solution is a solution. A nourishing mixture of water, sugars, salts, amino acids, vitamins and minerals. Once it's got all the nutrients it needs and is warmed up to a cosy 30 degrees Celsius, the yeast does what comes naturally. It starts feeding and fermenting, producing CO2. But thanks to its modified DNA, it also does something rather unusual. It secretes insulin molecules. At Kalundborg, they've taken the process that Jana demonstrated in a glass flask and repeated it on an industrial scale in this massive 200-meter long production hall. The modified yeast is added to large sterilized stainless steel flasks containing generous quantities of water, nutrients and sugar. Warmed to 30 degrees, the resulting fermentation broth is left for 72 hours for the yeast to go to work. The problem is, after 3 days, the yeast has produced just a few hundred grams of life-saving insulin, and that's mixed in with tens of thousands of litres of this murky broth. So they need to purify it. Purification begins with a spin in a centrifuge, filtration and a 24-hour stint inside a capture column.
In this capture column, we go from this solution to a clay graze-like substance containing 80 to 90% insulin.
After a second round of purification, the insulin needs to be dried. But there's a problem. Most dryers use heat. But the precious insulin degrades under warm temperatures. So they move it to this sci-fi drying room, where it dries at just above freezing for 24 hours. Now it needs to be bottled before being dispatched to doctors and patients. But the bottling facility at this plant looks like it's from another dimension. If Stanley Kubrick ran a factory line, this would be it. They start with powdered insulin. A typical dose weighs just 1,000th of a gram. Incredibly, this flask contains enough to treat one person for over 2,700 years. But before anyone can use it, it has to be diluted with distilled water. Then sent down the line, ready to fill thousands of glass vials. To ensure they're contaminant-free, the vials are washed, dried and sterilised at around 300 degrees Celsius. Insulin needs to be dispensed with an accuracy of millionths of a gram, so the vials are filled with computer-controlled precision. They're then fitted with an aluminium cap before passing through a rigorous scan and cam check. The final question is how to administer the insulin to diabetics. The answer is with something called a pen. But you wouldn't write with this. It's a needle and distribution system in a handy plastic tube.
Okay, so from these videos, you can see this is the manufacturing process. We're going to get this insulin from very beginning, from the just one vial of this kind of cells, just the 1 ml of the liquid. Then you put into the big tank, and you can produce enough cells, and then you produce enough, proteins. And then after that, we normally call this process is upstream process. Basically, you're going to grow cells, get the product, and then you're going to go to the purification process. You need to purify it because enough kind of fermentation broths bring you to there, and they have a lot of impurities, and that's you kind of use that when you take your patient taking them out. So you have to purify and get the pure insulin out. And then you're going to freeze it and dry them, and then you're going to formulation, to the formulation stage, and formulate into the liquid solution, and going to the individual kind of vials. We call that is a packaging and finish stage. And after that, obviously, you're going to ship to the individual kind of the pharmacy source. So that is the insulin. So obviously there are so many different types of biopharmaceuticals. The second type of the pharmaceuticals, that is the monoclonal antibody. So that is currently is the mainstream in the biopharmaceutical industry. So this is the structure of the monoclonal antibody. They have the two heavy chain and the light chain, and you have the tag area around here. So that is the genes you want to tag. Put into the this kind of plasmid. The two plasmid, one is for the heavy chain and for the light chain, and then you can design the one. And then you're going to use this kind of the designs put into the cells again. But this time, because antibodies quite often is they have very complex structure, especially for the sugar structure. We cannot use very simple like yeast or cells to produce them. We have to use we call it the chew cell. It's a chance hamster oval cell lines. Basically, it's a cells. Basically, that's the cells, and we can grow this kind of the. We can put this kind of the structure into the cells, and then they're going to express this kind of the antibodies. Okay. So the similar kind of way we're going to put the genes into the cells, and the cells are going to grow and express the proteins, and then after that we're going to purify them and get the pure non-antibody out. Okay. So this is the other type of this, all different types of the biopharmaceuticals. You can have the enzymes, or you can have the, different kind of the insulins or growth factors. So obviously, these different types of biopharmaceuticals will have different kind of the manufacturing rate. We talk about this is the insulin and the antibodies, but often we use cells, artificial cells to grow them, and then you can harvest and purify them. Also, you can go through different kind of the hosts. You can go through the plants, like you Nari mentioned about. You can grow all these, plants. You can produce this kind of therapeutic proteins and harvest the protein, these proteins, and you purify them, and you can get the product. Or you can get from the human plasmid, break down plasma, and then you separate all the different kind of the growth factors or the factors or proteins, antibodies, IgGs from the plasma, and then you purify them, and you can get the good products as well. So they're very different way. Another way is, for example, some proteins you can just use them this what we call the transgenic animals, like the sheep. You put this this kind of genes into the animals, and they're going to produce in the blood or produce in the milk, and then you can purify them later. So it's a different way. You can just produce them, but the mainstream is using cells. Just to use cells, grow in the big bioreactors, and then you can purify them. So just some of the very quick go through this kind of the biopharmaceuticals, but often they are big molecules. So big molecules, they're very difficult to produce. Okay, because they are big, and the cells can it's more difficult to handle all these kind of big molecules, because the molecules has been synthesized in the cells, and then they can excrete out from the cells with the correct structure. And also, there's quite often the structure itself is very complex. Okay, if you compare to this kind of aspirin, from here it's very, very small, just one benzene ring from here, very simple. But if you look this protein from here, for example, just the EPO, if you look from here, so they have alpha, beta shape, or all this kind of the protein structure, 3D structure. Okay, so it's getting more complex. Obviously, it requires cells to actually replicate all the structure inside your cells. Okay. Obviously, they're very expensive. From Nara's slide, I've seen that all this figure from here. So often the sales price from here is 2.1 million for the 2.1 million for this kind of dose per dose. So quite often, around probably 15 to 20% of the cost will go to manufacturing. So in other words, if we can reduce the manufacturing cost, we can reduce the follow sales cost. Okay. So for the currently we have the B-Suite students. They are working on this kind of project, trying to see what kind of way we can produce this kind of products with a very cheap process. So this is the Mac product. So this is the first product. I just use the first product as an example. Humira. This is the basic selling kind of drugs at the moment, Mac drugs. So you will see this kind of price. It's nearly double. You will see this one just the relation from 2005 to 2015. You see the price just the program is double. Okay. So that means this product itself has any improvement. That's the same product, just the price just double. Okay. Because more get more patients and the those more kind of products. This pharmaceuticals are growing, as I mentioned. Now, it's not only just the using antibodies, insulins. Now the market expanding to the cell therapy, gene therapy, all kind of new kind of the modalities for these pharmaceuticals. So this is just the number one here, 405 kind of the Indians in 2024. So that is the next generation of pharmaceuticals. We will cover from very small kind of the small molecules peptides, going to the therapeutic proteins, novel antibodies, biospecific, and now going to the CAR-T, going to the peg-body or this virus for vaccine, for example. So this is a very different types of kind of the generation of this, the new generation of the biopharmaceuticals. What are we going to do for is the bioprocessing people? So if you have a product, very wonderful product, you have this idea, so you come from here, you can have the drug discovery people have, get this kind of the type of product. And for bioprocessing people, what we're going to do is we'll start from here, we're trying to identify how we give the manufacturing, what kind of host we're going to use, host cells we can use. We're going to use bacteria, we're going to use plants, we're going to use transgenic animals, we're going to use Q cells, whatever we're going to find out first. And now we're going to say what kind of the process we give to manufacture in large quantities. So in the early stage for antibodies, so because the expression title is very low, so quite often you need a large, very large kind of the volume to produce the same amount of the product. But now because the expression title increase, also the volume decrease. We also will have a different way to improve that one, but what we have to find out is what is the basic expression system we have to use, and we can get the basic product out. And now we're going to figure out, what kind of the purification process we have to use. Okay. For example, the ECI cells, we have to get rid of the endotoxin because that is the can kill patients. But for the Q cells, for example, for mammalian cells, because they can produce a lot of virus particles, we have to get rid of all these kind of virus particles, otherwise the patient is going to get a lot of the immunological responses from that. So FDA have very, very strict kind of the requirement for any kind of residue for the virus particles inside of this kind of product. Okay? So for different kind of host cells, and now you're going to have a different way to purify them. So that is so process people are going to start from here. They're going to try to define this process first, and then they're going to start to produce very small quantity of the materials, and then people can do the clinical phase 1 and phase 2, and so basically that is the first initial kind of process. And after they get this kind of process, and if the clinical trials goes very well, if you're going to the clinical phase 3 or phase 4, and now you're going to manufacture big, large quantities. So again, now you're going to improve your process. At this stage, after you get all these kind of things done, really you have to lock down the process. Basically, you don't have, you manufacture these products, you have process, and you lock down this process because you cannot change the process in the future. Then you're going to submit to FDA and file this product, and they get approval, and you can use that locked process to start manufacturing product. Okay? So bioprocessing people will start very, very early stage. When you start the clinical trials, first you're going to start taking, start manufacturing this kind of product. The only difference is at the early stage, you only manufacture very small amount of the materials. In the later stage, you manufacture large quantities for the clinical phase 3 or 3 and 4. But obviously, if you get approval, you go into the market with the manufacturing stage and manufacture even large quantities. Okay. So that is the job for us, is really translating the discovery in the life science into real products. It's this kind of the engineering principles. But the other thing you have to, what the people have for the engineering people have to keep this in mind is the process has to be good, has to be cheap, way manufactured. So that is the always we have the business part in this kind of the biopharmaceutical process. Still need to know what is the basic business model, what is the model, way you can improve the product, but also reduce the manufacturing cost. So as I said, we have able to manufacture this kind of product, but at the different scales, from very small scale to very large scale, and this process has to be scalable. if this process at the small scale and very different from the large scale, also that is not scalable, and then you're going to trouble to translate your, any kind of process from the small scale to the large scale. So this is the scales. It matters. So think about it. It's a simple, easy way. If you have a shake flask here, you put the cells inside, you grow them. It's very simple. You can shake and you can get everything done. But if you're going back to the very large, so this is just a 50-liter single use bioreactors, you will say this is a very complex type around here, control system, this control system here, pipes around here. So you will say very completely different. So as a bioprocessing people, you have to design, figure out what is the best way to supply all this kind of thing, control the parameters, and you have to make this kind of process always reproducible. And then each time you have to control the process and make this process make this kind of similar product each batch. So that is you will say very, very different, from the very small scale to the large scale. And I just give you some scales, very, very interesting figures you will see from here. So insulin is run here. So because the insulin from the yeast, look at videos of the baby pig plant, they only dedicated to produce insulin. So that's why you can produce very, very large quantity is run here. So that is can produce probably up to 10,000 or maybe kilogram per year. So if you look at scale run here, you will say the price also is cheap per grams. Okay. But if you can produce very, very small amount of the materials, like this factor A, you will see right here. So now you will see the price is, I don't know, that is the 10 million per gram. So that is the very, very high numbers. If you just compare, I just use as numbers. It's a reference number here. That's a diamond. You will say it's much, much expensive than whatever you can buy. For the diamond case around. So really, it's going to what is the best way we could find a way to increase the scale, shift this one to this side, and then you're going to reduce the cost. Okay? So this is the so that's the insulin. So all this stuff from here, the red point from here, so that is the maximum antibodies. So again, because the antibody is the mainstream and we have very good manufacturing platforms now, you can produce really large quantities. And again, you can see that's kind of price going to around 10,000 per kilo. Okay. So for some of the molecules, but we cannot do anything because the expression type is extremely low. You have to manufacture very large quantity of volume, and the manufacturing cost is extremely high. Okay. This is just to mention. This is a platform for the manufacturing process. So normally, I just start from this bioreactor, big bioreactor right here. Before that, you have a lot of this kind of stage here. Okay, a very, very long process. You start from a 1 bale of the liquid. You have to expand to this one here, bioreactors. The maximum now is probably 100,000 liters. So that's a deeper volume in this bioreactor right here. So after you get this around here, you get the mag from these bioreactors, and now you're going to go to this kind of the process from here, and going to you harvest your product, you purify your product, and now you're going to finish kind of packaging finish from here. As I said, and because it's kind of Q cells, they're going to produce the virus from their own cells. So that is we have very dedicated kind of the process. I have to get rid of the virus particles, like detergent, like low pH, like virus, like filtration. We have to use a very dedicated process trying to get rid of them. Even they will not generate any kind of value for the product itself, but safety point, we have to do it. Okay. So this is the real process from very beginning to the end. Okay. So for any kind of student in this kind of program, they have to learn how to, design, understand each operation there, and understand how to design this kind of process, how to, understand all the process parameters. So for any one of this, like this kind of this bioreactor from here, any kind of the bioreactors, the operation parameters can be up to 20 different kind of parameters, variables you have to control. And you have to manipulate this kind of the variables, and so you get the best product. Okay. So that's his property. What I'm going to cover? Yeah. So that's his what I have for the manufacturing process. Any questions? Less than 40 minutes.
Yeah.
Less than 40 minutes.
Less than 40 minutes. So I mean, how much do our so we train about 40 to 45 students a year to go into this process. What are their average salaries when they start?
Better than me.
Yeah. It's complicated and technical, but let me ask you another question. For how many people do companies like Amgen or large companies employ in broadly bioprocessing, biomanufacturing? They're pretty big. What percent of they're
38% of total for this kind of big companies, for the first project.
Yeah, so about 10% of the company, so they have 8,000 people, so they have about 800 people in this area. This is why our average Inman students are getting 2 to 3 job offers each. How many competing programs do we have in the country? There's like 2 or 3, right? I mean, very few.
I mean, very few, but they're expanding now.
Yeah, we got to consolidate. Somebody we know well is starting a program in
But
Philadelphia.
we're still very unique in the west side, west coast, at least in the west coast. We are the only one.
Yeah, we're the only one on the West Coast. We're the only one that has the perfect corporate partnerships with this program that leads to the project. And I just hope you see, like compared to what I teach and Scott teaches, kind of fun. It's kind of fun business stuff, which is also technical at the end, doing the actual research is technical. This process engineering stuff, it's very specialized. It's very hard for universities to build up expertise in. And it's something we have this huge advantage, and that's why we have 65, 80 students every summer on B Suite, and we have 45 students every year on the program, because it's just a sure path to an awesome job in industry. It's just really one of the best things we're doing in this school. I personally think, I like the fact that it's a hardware technical degree, but it draws on our business program. There's a heavy quality regulatory affairs part of this, because all this stuff that goes in the companies is regulated because they're making drugs. So they take other parts of our curriculum, the finance, the accounting, the regulatory business. But at the end of the day, they're engineers doing this, and it's just crucial that this is working at KPI, and we're really, really thankful.